Yeah.
Stop it now.
Today and throughout this project, my focus will be on one of the most physics-reliant sports on the planet, snowboarding, and specifically how a snowboarder gets from the top to the bottom of the mountain using forces of friction, and how to solve for that using two different formulas while yielding the same answer. And then hopefully you can take from this, if you're a skier or a snowboarder, how to change numbers, varying forces to get you slower, faster to the bottom of the mountain, and hopefully a safer way down the mountain. The first scenario we will be facing here is how our friend Ezekiel, the man in the blue right here, will get down the mountain. And we will do this by finding out the forces that are in play, and we will eventually be able to solve for his speed at the bottom of the mountain or how long it takes for him to get to the bottom of the mountain. Now, the four main forces that will be in play are force of gravity, mg, cosine of theta. The force of gravity, because he's on a slope, pulling him down the slope, mg sine of theta. Force of kinetic friction, trying to keep him in place on the mountain, which there will be very little because he is on ice/snow and his board is very well waxed. And then the normal force, which is the reaction to the force of gravity and him pushing off the ground. Now, there are two ways of solving how the snowboarder can get from the top to the bottom of the mountain. The first way being through energy, and particularly through gravitational potential energy and kinetic energy. And by solving, I mean making it so we are able to find his final velocity or how long it took him to get from the top to the bottom of the mountain. Now, the energy formula means taking his gravitational potential energy from the top of the mountain, which we are setting to be 2,000 meters, equal to the kinetic energy at the bottom plus the heat the heat created throughout his run down the mountain, and that being generated through friction. Now, his gravitational potential energy at the top, as we know, is mgh. I will substitute the numbers in later. Set that equal to 1/2 mv squared, which is the formula for kinetic energy, plus absolute value of the work of friction, which is heat. And so, if one more substitution before we plug in the numbers, or before we substitute the numbers. The work of friction is the coefficient for kinetic friction, which is 0.15 here, times the distance traveled down the mountain. It's a d. Okay, and so now I will solve using just the variables, and I will plug in the numbers. So right here we can already cross out the m's, and then if we're taking it further we can go g8. Okay, and then the next step, left out the m. I apologize, f of k is the force kinetic friction, not the coefficient. So equals 1/2 mv squared plus f of k times d can be changed into mu sub k, which is the coefficient of friction, which is 0.15, times mg cosine theta for the downward force, the gravitational force into the ground, times d again. So mg cosine theta times mu sub k can be substituted, set equal to overall force of kinetic friction. And then we can cross out the m's, get rid of the masses as they are in every one. And from there, if you would like, we can solve it with for actual numbers. So 9.8 times the height, 2,000, equals 1/2 his velocity, which we do not know, plus 0.15 times 9.8 again, and that reminds me, or the angle that the mountain's at. So what we'll do now, show you how to solve for distance. this angle we're going to set equal to 50 degrees. And then the height, as we know, is 2,000. And so to find the hypotenuse, which we'll set equal to x, as you know, we take the sine of 50 equals 2,000 over x, which happens to be 2,610 meters, or 0.81 meters, if we want to get specific. So go back, and so multiply that by the cosine of 50, which is 0.64, times 2,610, and then just solving from there, 9.8 times 2,000 equals 19,600 equals 1/2 v squared plus 2,255. And then subtracting 2,255 from 19,600, multiplying by 2, taking the square root of that, we get the final velocity to equal 186.25, or put that in a better place. And then the second way we have is by doing it through, which is F net equals MA. And so how we can go about solving this is same values, height of 2,000 meters, weight of 60 kilograms, coefficient of friction of 0.15, kinetic friction of 0.15. So F net equals MA. So the F net, as we know, pulling down on them, is mg sine theta. Set that equal, subtract the force of kinetic friction from that, and then set that equal to mass times acceleration. And then, as we know, force of kinetic friction is mu sub k times the normal force. But just to avoid another step, the normal force is, as we went over earlier, mg cosine of theta. So minus mu sub k mg cosine equals to MA. And then from there we can cross out our 3 m's, and now we just have all of that. And then a formula that we learned in chapter 2 about constant acceleration, v squared equals v initial squared plus 2a delta x. Just a slight rendition of that, v final squared minus v initial squared equals 2a times the distance, which is the same as delta x in this situation. Then v initial squared equals 0, so we're left with that. And then plugging in for acceleration, we have, I'm just going to get rid of the f since we don't have an initial, v squared equals 2d. Plugging in for acceleration, we can use g times the sine of theta, which is the downward pulling him down the slope. Subtract from that the force of friction pulling him back up the slope to get the net acceleration. So mu sub k g cosine of theta. And then, actually we can get it looking very similar to our energy formula. If we, actually the exact same as our energy formula, divide this 2 over, so 1/2 v squared equals d, and then even skipping a step there, not skipping a step, but when you multiply d to both properties, or to both formulas, d times g sine theta, you just get g times the height, because d times sine of theta, as we showed earlier, reveals the height, or actually we showed the hypotenuse, but if you reverse it, it would reveal the height. So from that, you can just get g times h. Then subtract d times mu sub k. I'm just going to put this in parentheses to make it a little less confusing. Mu sub k g cosine theta. And now all of a sudden, if you go back, you would see down here we have you would see right here, 1/2 v squared, if you kept that there, equal to gh, which is what we have in the first one, and then subtract this mu sub k times g cosine theta d to the other side, you would get the same exact formula as for Newton's second law. If I were to plug in the numbers, I would get the exact same answer. So that just goes to show that Newton's second law will reveal the same answer in this case for getting the snowboarder down the mountain as energy. So you could use either equation if you want. That pretty much sums up how the forces of physics are involved in getting a snowboarder from the top to the bottom of the mountain, and how to solve for the final velocity using either an energy formula or Newton's second law, while still yielding the same answer for 186 meters per second as the final velocity in this situation. However, I forgot to say meters per second earlier, and Mr. Perry, because Doodlecast is kind of stupid and does not let you edit the video more than 30 seconds of what you've recently said, was not allowed to change that. But that speed's obviously way too fast, so we'd have to implement carving, which is basically like doing a sine function down the face of the mountain, which allows for varying coefficients of friction as well as making the journey longer. I don't have time to discuss the physics of that during this project, but I hope you learned a lot from this video, and maybe you can take this information with you to the slopes next time you go.